Our next speaker is Court Edmondson. He graduated from Auburn, and he's done a number of things, exhibit design, manufacturing, management positions, and he's been working with NASA on various contracts with Jacobs and now with Oceaneering Space Systems. All right? He's worked with humanoid robots. He's interested in spaceflight certification, and he works with meter-class telescopes. I assume that means big telescopes, 3 feet or more in diameter. Anyway, here's Court to tell us about the Valkyrie.
Good morning. Definitely not going to keep you in the lunch because I'm not interested in upsetting an entire room full of people. I'll try and tie together some of the things that Dr. Ambrose and Dr. Hembekin stated earlier, and I'm going to focus around the Valkyrie robot, which is one robot that Kim's already introduced to you. And I'll start off by talking a little bit about NASA's primary mission, which is exploration. Kim's already touched on that we're looking at doing, there's been various plans for habitats on Mars, deep space gateways or Lagrange points, and obviously we all believe that caretaker robots can play a huge role in helping us get those set up. But I wanted to pull on one thing in addition. Generally, all these plans have a timetable that's around the 2030s. I don't know about you guys, but that's coming real fast. I've got 3 kids, and they're going to be in college right at that time frame. So as a person that works with robots every day, I see that horizon rapidly approaching. And so that's something that can keep me up at night sometimes. So as we all know, robots are hard. Dr. Harmon mentioned that earlier. Even simple robots that look very benign can take a lot of tuning and a lot of research just to figure out how to make it do some fairly simple tasks. If you could play this video, please. This is a video, you can find it on YouTube. Just type in DARPA Robotics Challenge Fails. It's kind of, a motivational video at times. Heavily interested in. Thank you very much. I apologize for the sound.
That's a program.
For the presentation or the video? Okay, thank you. But we need a lot more brilliant minds working on this problem. Just the few that we have working on it at NASA is not going to help us achieve this timetable in the 2030s. So we're working very hard to get a lot more robotic research institutions to start working on things like Ross, as well as working with a robot such as Valkyrie within their facility. So how can we get, that leaves us with a question, how can we get an expensive long-lead robot in the hands of research institutions for them to use and experiment with? And the answer is something that Kim has already started being the lead on for the Space Robotics Challenge. We've built 2 robots, and they're in the hands of MIT. UMass Lowell and Northeastern are partnered together up at the Nerve Center. And we've also built one for the University of Edinburgh. They've acquired one, and they've been doing some wonderful research with it. This video, which again I hope is muted, it shouldn't have any corny music with it, at least. This video from the University of Edinburgh shows some of the work that they've done with it. They've done a lot of work on doing step planning, on actually using the arms to avoid objects that are in front of them so that they can pick up things around it. So they've done some wonderful work to help advance NASA's goals for using some of these caretaker robots. But the cost has also been a little bit prohibitive to open this up to more universities. So here they've done some perception for locomotion. And you can see here, this is what the robot sees. And it's planning its steps, moving around. This is one of the later versions of the IHMC software. And then here's some work on collision-free motion planning. And again, this is all using raw software coupled with IHMC's locomotion software. So this has been wonderful that we've had 3 universities essentially multiplying our workforce here at JSC to help us learn how to better use this robot and how to better prepare this robot for some of NASA's missions in the future. But we need more, and the cost has been very prohibitive to send it to more universities. So how do we get around this problem? And the first is we need to corporate institutions need to help reduce some of this burden on NASA. NASA's brought this robot amazingly far and made wonderful strides with it. But now it's time for some corporate partners to come in and learn how to make this robot cheaper, replicate it, and make it easier for research institutions such as UHCL or any other research institution have access to some of this hardware. We need to reduce the cost, redesign some of the really expensive parts, remove things that might not be necessary to achieve our research goals here in a terrestrial application, and then we can add that in as we get closer to the finality of the mission. And then, of course, as Henry Ford proved to us over a century ago, let's make lots of them. The more you make, the cheaper this robot will become. And as I mentioned before, let's help industrial partners identify academic partners that we can all work together with. The most important part about this is really what Ross is centered on. We need to share the research. If all of the research institutions that are working with a Valkyrie robot are able to share their information amongst each other, as well as NASA, of course, we could see exponential increases in how well the Valkyrie robot moves, as well as other caretaker robots in the future. Sometimes it's a bit difficult for a lot of research institutions to understand what the benefit is for having a piece of hardware like this. To some, it's very clear. But the Valkyrie robot can support multiple research objectives. From what I've seen traveling around to various colleges and universities, a lot of these institutions, they'll get pigeonholed in one of these 3 areas, and they might have 2 or 3 professors looking very hard at mobility, and they'll put together a small robot to help them test 1 or 2 things. And then you'll have another few researchers looking at manipulation, and then more looking at perception. And they're all generally making their robots to test out their own projects. Valkyrie is a diverse platform that can cover all of these objectives. So you'll have less downtime on specific pieces of hardware, as well as a piece of hardware that is state of the art and designed to be used for a high percentage of time. We've got good data from the other 3 universities and from traveling this robot around the world about what breaks, what doesn't break, and what we need to engineer to make better. So it's proven to have a lot of uptime for universities. Also, research institutions are able to leverage the Valkyrie robot to help build their program. Northeastern University is a very good example of this. They were awarded their Valkyrie robot for the Space Robotics Challenge, and they've written several proposals utilizing that robot for totally unrelated things. They've won a proposal from the Department of Energy as well as other sources. So they're using this robot to actually help build their program and cultivate a stronger program in their university. And of course, with what we're doing here, UHCL can play a role in that ROS development, so that's pretty exciting. And to finish, I just have a few statistics and requirements, and I'll take some questions if y'all have any questions about the Valkyrie robot. But she's roughly 6 foot tall, just a little bit over that, under 300 pounds, and 44 degree of freedom, all electrically actuated robot. We don't have any hydraulics or liquid cooling on the robot right now, and that's because we've always kind of had an eye towards space applications where hydraulics just don't really work that well. We have 2 computers. One is devoted to ROS and the other is devoted to IHMC's controller because we marry those 2 languages on our robot. And all you need is an overhead gantry for 1 ton and 208 volt 3-phase electricity. So the robot is pretty portable. One of the wonderful things about this robot that we were able to incorporate above and beyond what R2 and R1 and some of those other robots are able to do. It's very modular. We can take an arm off this robot in 2 or 3 minutes with 1 electrical connector and 1 bolt, and you can have another arm on there inside of 15 minutes, and that can be done by a trained technician. You don't need an army of engineers sitting there understanding how it works with the robot. So it's pretty modular. You can take an arm and a leg off in that fashion, and the entire computing system can be removed and replaced within an hour as long as you have a spare arm. So that's it. Any questions?